Good morning, everyone. Thanks for joining us. We are Richard, although, hopefully he can join us later for the Q&A session. I am Felix Cuadrado, and my colleague is Ben Stier. We will tell a little bit about us very soon now, but basically we have been the three graphiteers that have been working this time to build this system that is called Raphtory, that we are gonna be presenting you today. So Raphtory is a system that cares about temporal graphs. And I imagine most of you are familiar with graphs, with networks. We use them to follow Twitter connections. We use them to track influence, to analyze and do matching between elements. But Raphtory specifically cares about time. And why is time something important? Well, because it gives us one extra dimension when we reason about temporal information. For example, if we have a user graph, a contact graph of who has been in touch with another person, which has been a very timely topic over the last 2 years, I can have one user who met someone else on Monday, and that second person did have another meeting on Tuesday with a different partner. Then on Thursday, they traveled to a different place and met with another acquaintance. But, unfortunately, it turns out that this person was infected with COVID on Wednesday. Well, an intuitive example in why adding time to a graph, so that it's a temporal graph, is a good idea, is that even if we have all those connections, that a traditional structured graph will tell you that all of them are related, in a temporal graph, we can actually reason about time. And we can say in this case that only people who were in contact after the infection point are the ones at risk, and the epidemic might spread over those links. So that's, in a nutshell, the key intuition in why adding time to graphs we believe is a very good idea. And actually, it's not only a very good idea, but it can be applicable to lots of problems. We have been working on social network analysis, and I will briefly give you a few examples of the type of results that we have achieved by looking at the alt-right gap network. We have also been looking at how, in the case of legal field and courts, verdicts and laws actually reference one each other, and we can see the influence and the evolution of this legal base by applying time to those connections. We have also been looking at a space which is very naturally graph-like, which is everything that has to do with transactions, and in particular, the vast and unknown world of crypto networks and all the transactions happening around them. We'll also be coming back to this in this talk. And to give you something a little bit more out of the blue, we've also been exploring how spatiotemporal graphs can actually work, and we've been applying some of those techniques to track actually seed movement and try to identify collocation or contact patterns among them. So I was mentioning at the beginning that we are Richard, Ben, and me, and Felix, and the three of us began in this project at Queen Mary University. This was 95% of the merit for this really goes to Ben. He was our excellent PhD student who started this work and built the first base version of Raphtory. And as this picked up some steam, we were supported by the Turing Institute, so that we got through 2 rounds of funding in the AI for Systems program to develop this system and also work on multiple use cases on different domains. The result of that is the platform Raphtory, which is open source, so everything we are showing you today is actually available for you to use in your own domains on projects. But I should mention that in addition to that, and in this case, in the case of Ben created a spin-out company, Palmtree, that is specifically focused on further developing Raphtory and building up commercial-level solutions on top of it. They've already achieved some success in attracting funding, and if you would be interested in knowing more about Raphtory, about the research we do, about the project itself, you know how to find us. So in this talk, we will have three parts. I will do the first two, in which we are first introducing why are temporal graphs useful, and then I will move to Raphtory, and I will explain you how these temporal graph applications can be implemented in a reasonably simple way with our software solution. In the final part, Ben will show you how this works in action. He will show you a demo of Raphtory analyzing, in this case, Ethereum transactions, and we will see then how all this can work at a large scale. To the moon! All right, so the nice thing and special thing of Raphtory is that it is a system that, it is the first system that manages to bring those two capabilities. I have already spoken about time and how timing graphs is very powerful and very still unexplored up to now, because we didn't have useful tools to actually play with it in a way. But also, to make our lives harder, Raphtory is also special because from the very beginning, we envisioned this only made sense as a highly scalable system that could work with big data, large amount of information. Because of that, I will get into this later, but basically, whichever data source you want to analyze, Raphtory can interpret it as a graph, and no matter how large your data source is, it can be millions or billions or nodes of connections, it will manage to load it and process it by splitting it and distributing across multiple nodes. So what can we do with this tool? Well, we can actually implement and run a lot of different queries that combine both the structure, the nature of the relationships and interactions in your dataset, with filtering, selecting, or specifying what is the temporal scope of interest that we want to check. So we could be saying, okay, what does my network, what does my graph look right now? And now, 10 seconds after that, we will be continuously updating our in-memory graph, and we can run the queries at any specific point in the present. We can also go back over history. We can see how this graph was looking like last week. Or we can actually look for the evolution of this graph. How does it change if we repeat the same analysis within hourly or daily intervals? We can also be looking at this information, and as we were mentioning, that time has this concept of sequence of actions, of influence in interactions, we can also explore the influence of those links to see whether some nodes are tainted or infected, to see whether we can find some combinations of paths that only exist within specific windows in time. So let's see how can we put this in action with two quite brief examples, and then we move on to understand how this can actually happen. The first example is based on a social network, which is the most well explored and most natural mechanism for modeling and capturing information as a graph. In this case, we have GAP. GAP is not a massive network. Here we say that it's a total of 19 million ports, which is really only medium data. Raphtory can handle much more than that. It is, however, a network of interest because in our data set, which spans 2016 to 2018, well, there was a lot of noise and a lot of concern about what was actually happening with GAP. And almost none of it was really nice, but it was a network populated mostly by alt-right users with an emphasis on free speech, and we were suspecting that there could be some correlation between GAP activity and some major real-world events that actually happened during this platform. So we used this as one of our first case studies with Raphtory. And in order to do that, well, we had to build a graph from those messages. GAP, in a sense, is very similar to Twitter. We just have messages written by a user, which might be replying or retweeting other users, and so on. And we did build a graph from this information in the usual way. Whenever a user replies or retweets or reacts in any way to another user's message, we build a link between those. We build a link between those users. Basically, we do call those links as a mention so that one user is interacting with another one. That, however, is the usual way of modeling networks and graphs. The moment we bring time is when we actually say, actually, this is not the actual single graph of everything that happened in graph. We could be considering a window of time of interest, T, and we could be building the graph that only considers all the interactions that happened within that window. You can think that a window could be 1 hour to just see very short-term immediate reactions to messages. We could be looking for more stable structures and longer-term interactions by expanding the size of this window to a week, a month, and so on. Each one of these different periods of time, of windows of time that we analyze, is actually going to create a different graph. So already with this, we can see that adding the time dimension converts this tool from only modeling and analyzing one single graph to analyzing a family as large as different types of windows we want to actually model. And of course, we will only consider whatever is inside the window of interest. For our analysis, everything outside bounds does not exist. Well, what can we see with this? I will not go into all the details, but here you can see 2 time series that show across our whole timeline from 2016 to 2018 what happened with gap. And each one of the lines that you have here shows you how can we track the evolution of each one of those different size windows. The red one is the shortest one, only a day. The biggest one, the blue one, goes up to 6 months. And well, overall, if we want to say whether gap as a network was growing in the number of users, of active users that engage with each other, overall, when we aggregate the data, it seems that indeed it is growing, although it's not clear whether there's a pattern. However, if we look at the shorter term windows, in particular the weekly one in this case, we do see some more clear bumps. And actually, if we check the news, there is definitely one clear link between one of those bumps and real life events like Trump election, the infamous Unite the Right rally, or some events in which Twitter acted upon some undesirable accounts and acceptable messages, which caused some migrations from that platform to Gap. And we did indeed manage to observe these results. So this is actually very, very simple graph analysis, but it already shows the nice properties of exploring the full range of temporal graphs. Depending on the type of graph, you will actually be able to find different pictures of your data. And you actually need to analyze and to combine all of them, well, not all of them, the ones that are going to be more meaningful for your data in order to see the wider, bigger picture of your dataset. The nice thing is that Raphtory is perfectly designed for that. The simple graph that I showed you in the previous slide would require more than 20,000 different runs or experiments to execute. And the Raphtory system is able to execute all of this in parallel in a way that can complete the results in your laptop in a relatively short amount of time. Just as a plug, if you are interested in this data set and the problem, we did publish our results in a paper on CSCW. But well, today we are talking about Raphtory specifically. So just to give you some other motivating pointers, if we now think about cryptocurrencies, in cryptocurrencies, we can build very clearly a graph of transactions. Each one of the points here is a wallet. Whenever money is moved through a transaction from one wallet transferred to another one, we define a link. And we can also identify the time, because we are using Raphtory, that actual transfer happened. Well, I'm not gonna get into the details of that. We will get into a little bit more on that later. But if we are willing to exploit the use of having temporal information for each one of those nodes, we can actually be able to analyze and to identify specific suspicious patterns. And one example for that is what it's known in the complex network literature as motifs. A motif is a pattern that happens many times inside a graph. And when we look at time, we can look at temporal motifs. Like, for example, we have in this case one node, one wallet, in which a transaction comes with a sum of crypto tokens, 12 Ethereums, and shortly after that, and the shortly after will be relevant in order to detect behavior, that money goes out and is spread among other elements. Well, there are many patterns like mixer services that they are in charge of trying to cloud and to hide many of the interactions for external observers. The good thing of having a tool that can detect and analyze those type of patterns at scale is that we can actually make feasible to identify many of those potential suspicious candidates and identify them to help tackle money laundering and fraud activities. This is the example of a split pattern. Another example would be a set of back and forth relationships in which we see that rather than having just one transaction, there is a flow of many back and forth interactions that, again, they want to confound any automated analysis pattern. But using the temporal constraint there can actually allow us to better detect it. All right. So now, after this view, hopefully by now you see that adding time to graphs is a very cool idea. Let's see how can we do it with Raphtory. In the case of Raphtory, we are going to basically be modeling all of those changes that are going to be happening over time to a graph. We are going to be viewing them or modeling them as a string. Basically, I was mentioning at the beginning of social networks as a very popular case. We were looking at Gap. Let's use Twitter so that we can have the most baseline example of a social network. Well, whenever we get a new message, Raphtory will interpret that message as one or more changes happening to a graph. We could have a node being created, another node being created, a connection being created between those nodes, a node's properties being modified, and also we could have changes that are destructive changes. The connection might be deleted. In this case, we can have one user who joins the network, another user joins the network a little bit later at T2. Shortly after that, because they are both PhD students at Queen Mary, they become friends. Unfortunately, as life moves on, one of them changes position and then they lose touch. They actually lose that connection, so it actually disappears. They are no longer connected. But a little bit after that, they catch up. They restart their friendship, and also we can track how the different properties of those elements change. The very powerful quality of Raphtory is that we will be keeping track of every single change that has happened across history. And whenever we run an algorithm, we will be able to, depending on which window or region of interest we are working on, we will be able to finally track and detect everything that happened. And that will be available for our analysis. So that is the temporal part of Raphtory. What about the big data part of Raphtory? Well, we achieve that by building upon the best accepted model for creating big data graph systems, which is a model commonly referred to as the think like a vertex or the gather, apply, scatter model. The idea of this model is that we are going to program our graph analysis functions from the point of view of every single vertex of my graph. I will not have access to the other to all the other vertices and all the other information, but each vertex will know who am I, what are my properties at this point, what is my history within this temporal window, and also who are my neighbors. and vertices are able to receive messages from their neighbors and also share with them some actual results. The powerful thing of this idea is that whenever we run our algorithm, this runs completely in parallel no matter how many vertices we have. It can be 100, 1,000,000, 20 billion vertices. All of them will run this same cycle at the same time. And as each one of them can only get so far, they are only aware of their neighbors, we will be able to run iterative algorithms where they do hop once for each iteration, that they are able to compute global results for all of my network. However, as I said, this is a very well accepted model. It was proposed by Google in Pregel. It is best known by Apache Spark and the GraphX graph analysis system. We have gone one step further because we enable temporal algorithms. And whenever we add the temporal aspect to this thing like a vertex idea, we are able to limit the messaging that we do within our node and their neighbors to only happen at links or relationships that were happening before or after the point that the previous message arrived. For example, here we have this node who was in contact with those other nodes at all those different windows. And again, we get this sadly familiar result by now. A positive test happened on Wednesday at 9 a.m. Well, if that happened to this node here is going to be potentially at risk if we look at the window of risk of the users who were before that, but this will not impact all the links that were in contact before the initial close contact propagator that was spreading the virus. So this is one of the examples on how what we can do with our algorithms does also go beyond what is known by the main big data platforms. And to wrap up all the possibilities of what we can do with time, up to now, I have told you about this graph event stream in which we do select everything that happens to our nodes, to the properties of our elements. But whenever we run the analysis, as we were doing in GAP before, we can say, well, I'm actually interested in what happened during Trump election. And then if we specify that, Raphtory will create a graph that is purely based on everything up to that specific point in time. Maybe I'm not interested in that point, but I am interested in a certain period of time. I want to see what was happening during the electoral campaign. So I set the start date, the end date, and I do run my analysis only within that part of the network. We can also specify that, and Raphtory will automatically filter my data to fit within those boundaries. Or, as I did so in the graph of the GAP analysis, I can also look for multiple batches. I can slice my data set across a 1 day, 1 week, or 1 hour window and automatically run the same analytical function for each one of the different temporal graphs that I have designed. Finally, a nice feature of Raphtory that we hadn't mentioned up to now is that as the actual set of changes is modeled as a stream, it could also be that the incoming information is also a live stream. I could be connecting to Twitter, to the Twitter Firehose, and in one of those cases, I can also define a live query. So rather than defining what is the point in time that I am interested on, I will be interested in analyzing results now and 1 hour in real time for now, and 1 hour later, 1 hour later, and so on. So again, another way in which we do have a lot of depth by exploring everything that the temporal dimension gives to us. So to wrap up my part, how does this idea actually fit, and what do I need to worry as a developer in Raphtory? Well, Raphtory is a distributed system that is composed of many moving multiple parts. Although you as a developer will only have to worry about writing small subsets of code that we will be seeing later. In the Raphtory architecture, we are interested in ingesting data in order to create our graphs. And Raphtory has a set of adapter components that they are called the spouts, that they basically know how to parse and how to process an external data source. It could be a CSV file, it could be files stored in a Hadoop distributed file system, Mongo or a MySQL database, or a streaming live source like, again, Twitter, like a Kafka topic. Each one of them will be connecting via a unique spout. And Raphtory already comes packed in with spouts for the most common types of formats that we are interested in processing. We as users, we don't usually need to worry about this. We only need to worry about defining the graph. Okay, if I am getting Twitter data, I want to see then who are my nodes, who are my edges, when is time, and where are the properties. This is what the graph builder function will actually do. And once we define this mapping, Raphtory automatically maintains and stores all this set of changes to all those elements on a set of distributed components called partition managers, that they do keep up my possibly growing amount of information across the cluster. With this, we have created our temporal graph. If we want to analyze it now, well, we will be defining analysis functions. And again, here, Raphtory does come with a large library of roughly 50 different algorithms, with all the most common graph techniques being implemented already, but you could also define your own analysis function, and all those functions that you express will be interpreted and executed and analyzed over the whole cluster, giving you back the results of your query. So then, how does this work in one example? Let's suppose I am working with Twitter and I want to analyze it using Raphtory. Well, in a case, I have probably collected a historic data set of tweets, maybe from the last Olympic Games, and I will use then the pre-built spout to load that data into Raphtory. What I need to do now is to actually interpret that data as graph elements, and I can write my own graph builder, in this case a friendship builder, that is basically the Twitter graph that we were talking about before. Whenever a user reacts or mentions another user, I will be adding them as nodes, and I will define a link with what they are doing. That's it. By defining this class, Raphtory will be able to load the graph with a data set no matter how big or how large it is. But those components are pretty much mix and match as you want. Rather than doing batch historical analysis, I can also reuse the same graph builder that I use to build this graph in real time. And then I can use a stream spout that connects to the Twitter API, to the Twitter Firehose, and I will be able to dynamically see how this graph is being built as new tweets are being received by my spout through Raphtory. And up to now, I have mentioned that one of the big misconceptions that we have found when building and learning about temporal graphs with Raphtory is that there is never one single graph. There are many temporal graphs for the same abstraction, and I would go beyond that. There are also many times many different graphs that can be created out of the same base source. For example, rather than looking at the user-to-user graph, I can be looking at the conversations happening during my dataset. And in those conversations, my nodes would be the messages themselves, the tweets, retweets, the replies, so that I do build the cascades of reactions and replies to the original content. And I can achieve that using Raphtory by replacing the previous friendship builder by another conversation builder that interprets those results. So that's the only part we need to implement, and everything else will be done by Raphtory. How does then Raphtory take care of all those events that the graph builder has found out of my dataset? Well, all that data is being stored into partition managers. And each one of those partition managers will be saving one fragment, one partition of the whole graph that we have here, so that everything that you see here vertically would be the whole dimension impact of the graph, And there we will have nodes, we will have links, and you will notice that some nodes are stored in one machine, other nodes might be stored in a different machine. Some edges will be local to the same machine, some other edges might be distributed. Well, fortunately, you don't need to be aware or worry about any of that. Raphtory automatically distributes the data, manages to send messages across the network so that everything is updated and our algorithms can run no matter how large they are. Then, to again bring back the time point, if we look at this specific node, the partition managers will save the whole history of this node. And in this particular example, we can see that at some point, this node had a new edge added to it. It now has 3 connections, whereas before it only had 2. However, later on in time, one of the original connections was lost. So now the graph is only the node is only connected to these 2. Well, Raphtory gives you access to this whole history of changes for my node, and moreover, it gives you fine-grained access to when those bits happen. If here I am representing what was going on in the graph at this point in time, well, this node was actually created here. And the new link that we are observing here, it was actually created at this point in time, whereas this top link was deleted at this point and not whenever we are looking. We do not lose any time resolution, so we can always have access to that during our algorithms. All right, then the final thing I want to introduce you today is how can we then go on and analyze this information, this graph that is being created and updated? Well, we will be doing it by following this think like a vertex idea that I had mentioned before. Basically, for each one of my vertex, I have access to its local properties, its local history, and I can communicate with my neighbors. I will build upon that by defining a flow of multiple algorithms. I will be able to run single-step functions. I will be able to write more complex functions that iterate a number of times, and I will be able to extract the results that I want. And to grab all this, as we have mentioned before, my algorithms can be executed at any point or range or set of blocks within my full history, at a set point of a certain window size, a day, a week, a month, or to be continuously updated whenever I connect to a live stream. So, as an example of something that can be computed with a one-step bit, like we have here, if I am node A, I am able, with one of our implemented algorithms, to get the clustering coefficient for each node, the average network degree, or do something like the count of triangles in which this node is actually part of. We can do that by each node being aware of who are the neighbors and sending that information to the base node, which will be able to reconstruct with that one hop further on its boundaries. Moving to more complex algorithms, we at this point move to iterations, and well, in this case, we need to compute global results in which every node can affect the results of the rest of the network. We have PageRank, which is one of the best known ranking algorithms for any graph, connected components, or well, a few very, very powerful community detection techniques that allow us to do clustering. And to give you an intuitive example, here you can see how something like the label propagation community detection algorithm works. We do have a network in which each one of my nodes does have a different label, which in this case is the color it's painted in, and at each iteration, each one of my nodes will share with all of its neighbors what is their current color, so that the node, after receiving all those messages, it will decide that they should also move to, in this case, lilac, because it seems to be the one that is best connected to itself. So it will update its color, and then in the next iteration, propagate those values to the rest of nodes. And that's everything I wanted to tell you on what's a temporal graph, why are they cool, and how can we actually model and use those concepts with Raphtory. I give now the floor to Ben, who will pick up from here and show you how it works with a real example.
Thank you very much, Felix. So I will just share up my screen quickly and move over. Can you guys see my IntelliJ window?
Yeah.
Perfect. Okay, so I will just have a quick dive into how this actually looks in practice. Don't worry so much about what's actually going on inside of the code. This is really just to give you a flavor of how this looks, the sort of amount of code that you need to implement if you want to run kind of a real example. So we're going to have a look at how you run locally on a laptop, and then how this will change if you're then looking to push this app into a cluster. So the first thing we see here is that, as Felix was saying, is that we want to define how we're going to get our data in, and then how we're actually going to build up that graph. So we define a spout. So this is a file spout in which we're going to be reading some Ethereum data. So in this, we're reading a set of Ethereum blocks in CSV format. We're then going to create a Ethereum graph builder. So this will take each of the individual transactions inside of our blocks, and it's going to convert these into the graph updates that Felix was talking about. So this is adding in our vertices, adding in our edges, and updating them, and so on. This is additionally taking a tag file. So these tags that we're looking at basically specify wallet IDs, and then what that wallet is out in the real world. So this may be things like exchanges, it could be staking sites, people that are accepting currency, different brokers and so on. And this will allow us in our algorithms on Ethereum to decide, where money is flowing into. Is someone sending the money to kind of turn it into fiat? Are they purchasing goods of it? Are they sending it to dark markets and so on? So once we've defined our ingestion pipeline, we're then going to call the Raphtory object, and we're going to specify that we're batch loading because we have the data on disk. We can also do stream loading. It's where we're pushing more information in continuously, and we give our source and our builder. That's it. So our Raphtory graph is now built. That's going to be ingesting the data and will be available to query. So moving on to how we're then going to submit an algorithm to this. For this example, we're going to have a look at running a taint tracking algorithm. The idea here is that we're going to follow the hack of an Ethereum exchange. So this is Upbit, which is a Korean exchange where $50 million worth of Ethereum was stolen. And this here is the wallet ID of the guy who stole that money. So we're going to start from this person here, and at the point in time at which the hack occurred. And then we're going to set a set of stop nodes. So these are some exchanges that are well known at which this chap has sent money out to. But we can also use the information in that tag file that we saw earlier to see, where this money is spreading out to and get new insights out. So once we've defined our parameters here, we're going to take our graph. We're going to specify a point query, which is saying run it at one single point in time. What Raphtory will then do is, so taking this timestamp here, we'll rebuild how the graph looked at exactly that point in time. And this is 3 months after the hack occurred. So we're looking, after this period of time to see where this money was propagated out to. We're going to specify a taint tracking algorithm, giving our parameters, so our start time, our infected nodes, i.e. our hacker's wallet, and some stop nodes. And then finally, we're going to give an output format. So in this case, we're outputting to Pulsar, which is your message brokering system, which is behind Raphtory. And we're going to allow us to pull us into a Python Jupyter notebook later so we can actually sort of visualize our output. So one of the big things, and there was a question on this in the Google Doc on sort of formats of output of Raphtory. One of the big things that we're trying to push towards is that Raphtory should be able to click into really any data stack, any ingestion pipeline. We should be able to pull from anywhere, but also push out to anywhere, so that you can really, make it as easy as possible to get your insights in and out using Raphtory. So delving a little bit deeper into the graph builder quickly. Again, don't worry so much about what's going on here, really just to see, how difficult this is to implement. For a graph builder, all you have to define is one function called parseTuple. This will take each individual transaction, and in this case, this is an individual string. We're going to split the line out, extract out all of our properties, things like our transaction hash, the amount of money that was sent, the wallet IDs, the time of transaction, etc. And then we're going to put that into a set of updates. So we've got two add vertex updates. This is specifying the two wallets, i.e. our sender and our receiver. Some additional tags, i.e. what these people are, if we know what they are. And then we're going to create an edge between them. So this edge will take information like the transaction hash, the block number, and the amount of money that was sent. And then, as Felix was saying, because we're storing the full history, if these two individuals are sending each other lots of money, then when we run our analysis, you'll be able to see the full history of these values. So all of the amounts that were sent between these two individuals. And that's it. That's all you really need to do if you want to convert this Ethereum data into a graph. Raphtory will do all of the distribution, all of the synchronization, and propagate messages around. So that's all you would need to do for a local runner. So this is your laptop version. If I click play, this will run, and you'll start getting some analysis out. If we want to switch this into a distributed mode, what we need to do is we need to define a Raphtory service and then create clients which connect to that service to run our algorithms. Now, basically, you can just copy and paste what you just saw into a couple of different functions. So given our Raphtory service here, we define a spout as before, so our file spout. We define a builder, which is our Ethereum graph builder. And then we specify in this case that we're batch ingesting because we have all of the data on disk. Once this is pushed out, so I'll get into this in a second, because this is all containerized, can be run via Docker, Kubernetes, etc. We then define a Raphtory client, so by raphtory.create client, and then we can submit exactly the same query to it. So point query, we're specifying our taint algorithm, the same output format, same timestamp, etc. For the taint tracking algorithm, I won't go super deep into this because it will take a little while to explain. But all of our algorithms, I think there's well over 40 now default algorithms are available documented on our website. If anyone's interested, I can delve into them with you. And it's very easy to also implement your own algorithms or expand upon the ones that we already have. So with that, I'll run into basically what this looks like on the other side. So as I said, we push this out to a topic in Pulsar, which is a message broker similar to Kafka. And this actually allows us to pull this down inside of our Raphtory client for Python. And the reason that we've pushed into here is because it allows us to take the data out of Raphtory, get it into data frames, and get it into things like NetworkX, the sort of usual data science tools that you see with graph processing. So as you can see here, I'm creating the Raphtory client. It's connecting up to Pulsar, to the topic which I've just created. We're going to then create a data frame from this. So you should see this come through now. And this will be all of the wallets that the money has flown through from that initial hacker's wallet. We can then build a graph from that and then draw that out into our window here. So obviously, the graph here is slightly small. This is definitely not the scale at which Raphtory is running at in production, but allows us to kind of visualize what's going on. So behind the scenes, what's actually happening with this deployment is that everything is managed by Kubernetes. So we can see here that you have all of the individual components that back up Raphtory. So these are things like Pulsar, Zookeeper, Bookkeeper, etc. That are running to allow communication for everything to be backed up on disk and your data to be secured. And then what we can see following this is also the Raphtory components, which are deployed via that Raphtory service that we established. So this here is the Ethereum graph builder which has come up that's going to be ingesting the data, parsing it, and then pushing it forward. Given that that's all running in Kube, one of the wonderful things is that we can also monitor how everything is running inside of Raphtory. So these are kind of the normal generic metrics that you'd expect. So we can see how all of the machines are running. So here we can see things like CPU load, the amount of memory utilized. We are in a memory platform. We're moving on disk as well so that we can expand past the limits of the devices that you have in your cluster. But we can also get very specific metrics out for topics. So this is for the spout, for the graph builder, for the partitions and queries, how many messages are being sent around, how well they're running, do we have any bottlenecks, what can be improved. And then finally, as a kind of an additional nice benefit to running on top of Pulsar, alongside this graph analytics that you're running inside of Raphtory, we actually have a SQL engine that allows you to query the stream of information that's flying in from all of these components. So in this case here, these are the recent 1,000 transactions that have come from the spout. So you can build alerting and other elements on top of this SQL interface, and then use that to run analytics or push for information further down your pipeline. So that's a very kind of whistle-stop tour over one example of how Raphtory runs. I'll then just quickly hop into what's on the horizon before we hop into some of your questions. So as Felix said right at the start, we've recently got quite a good amount of funding, both for Raphtory and for Pometry. And on the basis of this, we've been rebuilding the platform on a much more solid ground. So you've heard me talk a little bit about Pulsar, which has allowed us to get up to about 1.5 million transactions a second, pushing our data through. We've also been building on top of things like Apache Arrow, which is a memory format which allows us to actually translate freely between Raphtory and Spark and Cassandra and basically the entire Apache ecosystem with zero copy overhead. And we're also looking to push this into things like NVIDIA GPUs, so we can do accelerated analysis on these very, very large graphs. This also means that we can store data on disk and that we can ingest very, very, very large graphs, so multiple terabytes of data if you so wish. We've been working very hard on some new APIs and tool integrations. Obviously, you saw a little bit here on integration with Jupyter, and we're really interested in hearing on the sort of tools that you have in your pipeline that would be very useful for us to integrate with, so to make your analysis easier. And then finally, because of this, these sort of grants and funding that we have, there's quite a few research and industry positions available for those that are interested. If you're interested in this sort of temporal graph space, please do reach out in this regard. And on this point, as a last element, if you are interested in getting involved in any capacity, if you want to dip your toe in and start speaking to us, please come and join the Slack. This link is also available on the GitHub profile page. If you want to give Raphtory a try, it's fully open source. You can come and download it. There's some instructions on how to install all of the components in the backend or to use the Dockerized version if you wish. And then if you're interested in getting Raphtory in your tech stack, if you have some specific use cases you think this would really solve, come and give me a contact directly or reach out to us at Pometry. And with that, I say thank you very, very, very much for listening and for joining us at AIUK. And I'd love to take any of your questions. That I shall end.
And while people are thinking of questions, thank you very much, Felix, for taking over from me at the last minute. I had microphone and camera problems, so Felix did very well with some slides that I'd made last minute tweaks to. So.
Wonderful. I think we've been semi answering some of the questions in the chat, but I guess we can quickly run back through, and I think there was a couple that we may have missed. I think
a question about the largest graph you could ingest, Ben. I thought you'd be the best person to answer that one.
Sure. So I think the largest network that we've been working on at the moment is the full Bitcoin blockchain network. So this works out something along the lines of 10 billion individual updates. And we're looking to expand past that as soon as possible. So the amount of memory that this requires at the moment is very large. And as I was talking about things like Apache Arrow, the idea here is that we can massively compress this down and allow this wide temporal analytics, so going back and forth at any points in time in a very quick sort of query time. So we're looking at seconds to build up the exact version of the graph, and then tens of seconds to run large-scale analytics across that network.
Moyen has asked us about the temporal part of it. So we can, you said cut time segments, analytics on just segments. We can do things like sliding windows, but also algorithms that respect time order. So tracing a link that's followed by this link in time is followed by this link in time. So that's how we use the tracing of money through time. So there's a lot of different ways in which the Raphtory can use time. Not just saying the graph at time t or the graph between two times, but also asking questions about how things can propagate, respecting time.
Yeah, so I think it's worth saying there that there's two levels of time that we have. So when you define an algorithm, so for example, the taint tracking that we had in my demo, you're only propagating forward in time. So if you receive money on Wednesday, you can only propagate, on edges that are from Wednesday forward. You can do things like, as Felix was discussing, explore temporal motifs. So like if Richard and I send each other money, 5 times over the course of a year, that's probably not very interesting. However, if, we send each other 1,000 times within 5 minutes, this is probably us trying to avoid some sort of large, transactions greater than $10,000 will get investigated, etc. So there's that kind of like historical digging in that happens on the algorithmic level. But when you go into things like running a query, so like a range query, you can take that algorithm and you can run it over hundreds of thousands of different specific views of the graph. So we had with the courtroom data that Felix was discussing in the first section of the talk, we had 400 years of data, and we were looking back 1 year, 5 years, 25 years, 50 years, and we can move through that a day at a time. And this is 750,000 different perspectives of the graph. all running exactly the same algorithm. And all you have to specify is one line. So this is a range query. These are the points in time that I'm running through, and this is the windows that I want to look back. And the algorithm will run exactly the same across all of those and output your results. I think there was one as well that just a bit up about weights and negative data from Stefano. So I think it's worth saying that the Raphtory model really can represent almost any network. So the kind of base version is directed. You can store any properties on that, so strings, integers, floats, doubles, booleans, arrays, etc. And these will all have historic properties. When it comes to your algorithm, you can then view those in different ways. So you may want to say, okay, I want to view this as undirected. That's totally fine. You may want to explode out your history so you can view each individual update to an edge as an individual edge itself and investigate your graph in that manner. So we're trying to allow the APIs to be as open for you to kind of build the exact model and the exact analysis that you want to do. And yes, we can handle negative weights. I just saw your second question. Okay.
Roman's asking what's the fastest we can update.
Yeah, so the current currently with the batch loader, we're getting something like 1.5 to 2 million updates a second with one spout. These can be parallelized, so you can have multiple spouts. You can have many graph builders and many partitions. When it comes to the streaming of data, so this is new information that's coming in from a stream. I think we've got up to about 600,000 updates a second, streaming off of different data sources. But I mean, it very much depends on what use case you have, how your data is formatted. So I think an interesting thing here is that your data can be ingested in any order. Because we have this temporal model, you can ingest everything in totally backwards and the same network will be built, even if you have deletions. So if you've got tens of data sources, blast them all through, wait for it to synchronize, and then, away you go.
Yeah. Of course, then, I think one part in the ingestion part, we can control that very finely. If we are interested in the analysis that we are doing, well, then the actual time is going to depend on how complex the analysis algorithm is. As I was mentioning, you can have a one-step analysis, which is pretty quick to execute. You also have an iterative function that may have to run through 10, 20, 30 steps. So, of course, then that's going to vary depending on that.
So I think we have a question here on infection spreading. So I don't think there's any specific signal prediction algorithms that are currently built in. It's definitely something that we'd look to explore. I think there's a lot of expansion that we can do, both in the available algorithms and in the APIs. So, for example, one of the things that we're looking to put in soon is if we're doing things like how bursty is an edge, how the transactions occurring between two people, for example, can we automate that process? Can we add functions in that allow people to do this? So if there are specific things that you want, please do get in contact from the algorithm. We have a full algorithmic team that can work on these side of things.
There's also a question about how does Raphtory compare to RDF or Neo4j? I think it compares in quite a few different angles. So once Neo4j and RDF-based databases, they are primarily databases that are designed to answer queries, and they are best designed to solve basically local scope queries. So I give you a pattern, and I want to give me all the cases in which a user has this property. Raphtory, you could run this type of queries, although at the moment we do not have a specific query language. We do not support Cypher or any of the other alternatives, although there are plans in the pipeline for that. But Raphtory can also do full-scale analysis that goes way beyond that, and we can run random walks. We can have some applications like PageRank or some type of clustering algorithms that they are not really practical to execute with those database-first systems. So you can define some queries in a database-first system that ends up doing this analysis, whereas we sort of come the other way around. You can define any arbitrary computation, and well, some of them will be giving you the same as those systems. Beyond that, Ben has a lot of experience with Neo, so I'm sure he can expand on this.
No, I think that's exactly it. I think that the graph space has an awful lot of database query focused platforms. What we're trying to do with Raphtory, alongside the kind of temporal first aspect, which is kind of unique to what we're doing, is focus on these very large scale analytics. So algorithms which include billions of nodes all communicating with each other. That are going to propagate information, and all of them return a result, instead of your query, which is like, go to this individual user, propagate 2 hops across, give me their neighborhood, this sort of information. So on Moyen's question here about the amount of users made the same pattern, yeah. So we actually have a lot of different motif binning. So if you want to find specific temporal motifs that people are using, then you can get this information out and aggregate inside of Raphtory or external to Raphtory, pushing it down your pipeline. One of the things actually that we found here was really interesting, looking at some crypto data, is you could actually see the mixer services. So these are services where people put their money into to hide where they're sending money out to. When their software updated, you could see all of these individual wallets instantly change the pattern that occurred. So you had this kind of change point in their history, and it made them stand out like a sore thumb. So you say, 100% all of these services are at least the same mixer, the same person is running them, because they're all, they get this update on a Friday evening and it all occurs, at the same time. So it's really interesting to see how this actually evolves when you push it out. On the point of a Neo builder as well, yes, I think this is we're just pushing out a new version of Raphtory, and then post that, one of the things that we're looking at doing is connecting to a lot of other graph systems. So at the moment, there's something like 70 plus connectors in Pulsar, so you can connect to all your normal databases, other streaming platforms, files, S3, all the cloud providers, etc. They don't currently have ones for things like Neo, Tiger Graph, relational AI, etc. But yeah, no, definitely we're looking to put those in and pushing back out to them as well. I think that's kind of an important point there. So we actually do. On Roman's question,
just start already.
We do have a node to vec algorithm. We're looking at lots of different sort of graph embedding algorithms that we can build on into Raphtory, and making these temporal as well. So the idea would be is that you could do your kind of large crunching of data on Raphtory, and then push that out to something like Python, where you can actually then push those embeddings into your machine learning and AI platforms that you're used to using.
This is something that Ben was mentioning, that there is work to integrate with Apache Pulsar, and Apache Arrows, and that would actually really help with that, because we could be able to hand that in memory without having to exit really the system.
Yeah, so the nice thing there, not to get too nerdy, is that the Arrow is a in-memory representation that basically lots of different platforms and languages agree to. And what that means is you don't need to serialize when going between them. So you should be able to move from Raphtory into something like Spark, from Raphtory, which is in Scala or Java, and go straight into C. And there will be no serialization overhead. So you should be able to effectively just pick up that memory from Raphtory and use it elsewhere. And so that the premise there is that all of the tools that you have in your pipeline that follow this standard should be able to move very, very quickly amongst each other. I'll just check the other doc quickly to make sure there isn't anything.
There's a question at the bottom about can the chain of money transfer be cut by transferring money to a hardware device out of network, like a ledger?
Yes, so I mean, we have on the Pometry team one of my co-founders, Harun Yusuf, who done his PhD in cryptocurrencies. or in crypto security. And this is one of the things that, when it gets use case specific, that we're looking at is like, how do we do cross-chain analysis? Can we do some inferring of, like, if we know this person has this wallet in Ethereum, this is the wallet that they have in Ripple, can we transfer the taint forward across these networks? These kind of multi-layer networks are something that we're investigating in the future, but it is not something that we're working on directly in Raphtory at the moment. There's a lot of companies that we're working with, and if you're interested in this, definitely ping us and we can discuss further. Wonderful. In which case, I think we're just over time. So thank you all very, very, very much for joining. The view counter was only going up, which I was keeping an eye on, which I was very, very happy about. It warms my heart a little bit.
Yeah, thanks everyone for being such a lively audience, giving good questions.
And if you're interested, please, it would be great if you join the Slack if you have some interest in Raphtory, because that is the easiest way to contacting all of us, and no question is done really. So this is pretty much work in progress. So we are really looking forward to any input.
Yeah, the Slack's pretty lively. There's lots going on, so it's a great way to find out about it.
I'll just paste the for those that are still here. I'll just post the link quickly.
Okay.
Cool. Thank you very much, guys.
Thanks, everyone.
Very soon.
Okay. Thank you.
Bye-bye.
This is the graph dog.
The graph dog.
See you.